you guys may or may not remember what stoichiometry is, but let's first write this, stoichiometry. And stoichiometry is using a chemical equation to convert information about one substance into information about another substance, right? So stoichiometry means it simply uses the mole ratio from a balanced chemical equation. From a balanced chemical equation. Okay, so that's what we're talking about. We're talking about those things where we use the chemical equation and we tried to take information about one substance and then convert it into information about the other. The difference in this case is that we're going to be doing this with gases. Okay, so stoichiometry is like when you have some reaction such as, I don't know, you were burning propane, say, and you said, okay, I have C3H8, which is propane, and it is a gas, and I am adding oxygen, which is also a gas, and I am going to convert it into CO2, which is a gas, and water vapor, which is also a gas. And now we have stoichiometry with gases, and we would use our balanced chemical equation. This is not balanced, and so our first step, as always, would be to make sure that we have a balanced equation. And in this case, you always balance hydrogen and oxygen, hydrogen and carbon, and then balance oxygen last. So 3 carbons on each side, right? We have 8 hydrogens, so 4 hydrogens over here, 4 H2Os over here gives us 8 hydrogens on both sides. 4 times 1 is 4, 3 times 2 is 6, so we have 10 total oxygens over here, and that would give us 5 O2s over here. So the first thing is we need a balanced chemical equation. Don't forget always to check to make sure that the equation is balanced. But then, if I wanted to do calculations, since these are gases, I would have to know something about the temperature and pressure. In this case, let's suppose that it was at standard temperature and pressure. Right? Now we can do calculations and we can convert information about, say, the amount of propane. Suppose I had 5 liters of propane, right, C3H8, and I wanted to know how many liters of CO2 I was going to be producing, right? So question, right, how many liters of CO2? And that would be a stoichiometry problem we could answer. So that's what we're going to talk about today. Now, if we take a look up here, there are notes, and these are provided in the module, but we're going to talk about these. There are 3 basic ways of doing stoichiometry. One of them is simply volume to volume, and this one is really, really easy, okay? And that's because of Avogadro's principle. Now, I keep on mentioning Avogadro's principle, but Avogadro's principle is basically V1 over N1 equals V2 over N2. In other words, if the temperature and pressure are constant, volume and moles are directly related. Well, so let's take a look at that, because our first problem that we were looking at, our sample problem here, was just that. This is volume to volume, in other words, liters to liters of gases at some constant temperature and pressure. And in that case, I know, because of this equation, that there is a ratio of carbon dioxide. I know that we can say 3 moles of CO2 for every 1 mole of propane. However, the beauty of stoichiometry with gases, if the temperature and pressure is constant, since moles and volume are directly related, I can simply say 3 liters of CO2 is exactly, it corresponds to 1 liter of C3H8. Right? In other words, that the mole ratio equals the volume ratio. And this turns it into one-step stoichiometry, which is pretty sweet. So I can simply say 5 liters of C3H8, make a fraction bar because I'm looking for liters of CO2. CO2. And I can simply, I'm trying to cancel liters of C3H8. I need liters of CO2. And I'll simply use that ratio from the balanced chemical equation, 3/1. And that would give me 15 liters of CO2. And so it's very, very easy stoichiometry, okay, because the volume ratio is the same as the mole ratio. So the easiest stoichiometry we could possibly have to do is one where we have, we're converting an amount of one gas into an amount of another gas. And the ratio, the example problem that's given here, we have butane, and it's being burned, and we're trying to figure out how many liters of CO2. And you can see that we use 8 liters of CO2 over 2 liters of C4H10, and that's because the mole ratio and the volume ratio are the same. Okay, so yay, volume to volume stoichiometry. However, just keeping it STP, when we were talking yesterday, we said that at STP, we always have 22.4 liters over 1 mole. In other words, 1 mole of gas is always 22.4 liters at STP. Now you have to see those magic letters, STP, in your problem for this to be the case. But that's one of the reasons a lot of problems are done at STP, because it allows calculations to be really easy. So that just means that we can use this ratio, 22.4 liters per mole, as part of our stoichiometry. So let's do a sample problem like that, and let's see what it would look like. So let's suppose we have some balanced equation such as, I don't know, let's suppose we have magnesium, metal, and we're adding hydrochloric acid, and it's a solution, and it is becoming hydrogen gas, okay, and magnesium chloride. And why did I make that HCl2? How embarrassing, HCl plus MgCl2. There's my Cl2 aqueous. So here's my equation, right? And let's suppose we have, say, 0.25 grams of Mg, and we want to know how many liters of hydrogen gas we're going to get. Well, the first thing I need is my balanced chemical equation. As we've mentioned, that is an important part of this. We have 2 hydrogens here, so I need 2 over here. I have 2 Cl's here. Well, I have 2 Cl's here. I have 1 Mg and 1 Mg, so this looks really balanced at this point, so yay us. Okay. Well, if I'm going to do stoichiometry, I will start with my 0.25 grams. Oh, and we'll make this at STP. So let's see if this problem is at STP. What do? Well, we start with our 0.25 grams of Mg, just as we always would. We have to cancel grams, and we have to go to moles. Well, once we see grams over moles, we know that this one is just going to be the molar mass from the periodic table. Okay. Then I'm going to cancel moles of Mg and get moles of H2. Well, that's what makes this stoichiometry. So this is the mole ratio from the chemical equation, right? And that one, if we look, right, there's 1 mole of H2. There's an understood 1 here, right? So 1 mole of H2 and 2 moles of HCl. So, and 1 mole of Mg. Whoops. Right, so it's 1 to 1. Really? Let's not do that. There we go. And so we can just put 1 and 1. Then I need to cancel moles of Mg, moles of H2, and I need liters of H2, because that's my goal. Liters of H2. So there I have it, right? And this one is going to be 22.4 liters per mole because it's at STP. And so this one is pretty easy because of those magic letters, standard temperature and pressure. Okay, so at this point I have 22.4 liters and 1 mole, and all I need to do is go to my periodic table and look up the molar mass of Mg and find that 1 mole of Mg is 24.31 grams. And now I have everything worked out, and I can do it on a calculator and say 0.25 grams divided by 24.31 times 1 over 1, and then times 22.4 would give me 0.23 liters. Okay? So about 230 milliliters of hydrogen gas would come from a quarter of a gram of Mg at STP. Okay? Because it's not that many moles, it doesn't make that many liters. But there you go. All right, so that's our second possibility, that we have STP and we can just use 22.4 in our chemical equation. The last possibility is the ugliest, and that is simply, what if we don't have anything special about our equation? It's not gas to gas and it's not at STP. Well, they have to give you the temperature and pressure to make this possible, but then you just use the ideal gas law. Okay, so for something like this, suppose we have this same equation and we say we have, say 12 grams of Mg at 1.1 atmospheres and sorry about this, 40 degrees Celsius, right? Then what would we do? Well, we do the same basic thing, except that we wouldn't be able to use 22.4 at the end. So what we do is the first step is simply find moles of gas. Well, that's only two-step stoichiometry at this point, so we'd say 12 grams of Mg times, and we can use the same mole ratio, 1 mole of Mg, or same moles to grams, 24.31 grams of Mg. We can use the same mole ratio because it's the same chemical equation, so 1 mole of H2 over 1 mole of Mg, and we just stop there, right? So 12 divided by 24 is roughly 0.5, but 12 divided by 24.31 is something a little smaller. So we get 0.49. When we multiply it by 1 over 1, we still have 0.49. So 0.49 moles of H2. Okay, that's what we'd get. Well, then the second thing is just use the ideal gas law, right? And if we do that, we know the ideal gas law is PV equals nRT. But what I want you to do is always rearrange it for what you're looking for. Since in this case I was looking for volume of gas, I would say V equals nRT over P, right? And so I can simply say it's equal to 0.49 moles, okay, times R. In this case, since I'm using atmospheres, I'm going to use 0.0821 liter atmospheres over moles Kelvin, times T, and it said 40 degrees Celsius, but I need to use Kelvin, so that's going to be 313 Kelvin, all divided by the pressure, which, as I remember, is 1.1 atmospheres. And so now I have the ideal gas law set up, and it'll give me liters. And so I simply say 0.49 times 0.0821 times 313 divided by 1.1, and I get 11.4 liters. Woohoo! Right? So that's the hardest of the problems. But it's the same idea, right? In other words, that we're going to use stoichiometry to find the moles, and then we're going to use some gas relationship to convert moles to liters. In this one, we just used the whole ideal gas law, but above it here, we just used sort of a simplified version of the ideal gas law because at STP, we know the ratio. Over here, we know that the ratio of moles and the ratio of liters are the same, so basically, I said that for every 5 liters there are of propane, there is some number of moles of CO2. I'll multiply that by 3. Since the ratio of liters to moles is the same for propane as for CO2, then I will simply convert back and get 15 liters of CO2. Or I'll go directly without converting to moles and say 5 liters times 3 over 1 gives me 15 liters. But basically I'm doing the same thing. I'm just sort of saying I'm going to convert this to moles, and I'll convert the moles of CO2 back to liters. Since those two ratios will be the same, I can just take the shortcut of saying liters to liters. Okay, which is kind of cool. So really, we're doing the same thing all 3 times. It's just the easiest is when you have volume to volume. All right. Anyway, so we've got some practice problems, and so let's see what we've got here. And you may notice there are 4 practice problems, but they come in varieties. So, like in this case, we have grams of aluminum, and we're trying to find hydrogen gas, and it's not at STP. I don't believe. And so, so we're going to use, this is like a type 3, right? This is like the 3rd type. It's ugly, right? We're going to find moles of hydrogen gas, and then we're going to use the ideal gas law. So, 2-step stoichiometry. And then the ideal gas law. And let's see, in this next one, we know temperature and pressure, and it's basically the same problem in reverse. So we're going from liters back to grams, so we'll just use the ideal gas law first. Right, and then we will do 2-step stoichiometry. So right? And then this problem here looks like we've got those magic letters STP, but it also looks like we're using volume of propane and volume of CO2. So this is volume to volume. So this is our easiest one. Okay. And then in number 4, it is also STP. But in this case, we have a liquid here and a gas here. So actually, this is oxygen and hydrogen. So this is also volume to volume. Volume to volume, right? And then, then it asks you for grams of hydrogen at the end. And so this is going to be using 22.4 liters per mole, okay? Because we're at STP. And so here's the basic logic of all of it, so we can see how we're doing it. So let's try this first one, the hardest one, together, and then I will let you puzzle on the other ones. Okay? So 2-step stoichiometry, I'm starting with a balanced equation. So I'm going to start with my 0.25 grams of aluminum. First thing I need to do is get rid of grams of aluminum and go to moles, because in stoichiometry all the important work is done with the mole ratio. All right. So then I will cancel moles of aluminum, and I will get moles of hydrogen gas, H2. Oops. It would help if I put the word moles in there, right? Equals moles of H2. Okay, so moles of aluminum will cancel, grams of aluminum will cancel. I'll be left with moles of H2. The mole ratio comes from the balanced chemical equation. There are 3 moles of H2 for every 2 moles of aluminum from the chemical equation. Here's my 3, and here's my 2. When I look at the periodic table, I find for every 1 mole of aluminum, there are 26.99 grams of aluminum, right? That's the molar mass of aluminum. And so now I have two-step stoichiometry set up. And say 0.25, and I guess I'll divide by 26.99. And I will multiply by 3 and divide by 2. So I get 0.014 moles of hydrogen. Okay, so there's my stoichiometry. Now, once I'm there, now I can use the ideal gas law, and I'm looking for a volume, right? So again, PV equals nRT, but I'm going to use V equals nRT over P. And I need to have moles, liters, atmospheres, and Kelvin, right? Unfortunately, they gave me millimeters of mercury, so I'm going to have to take a brief moment. They say 740 millimeters of mercury times 1 ATM over 760 millimeters of mercury, because I looked at my table of standard pressures, and I know that that would, that would give me atmospheres. So 740 divided by 760 gives me 0.974 atmospheres. So this is going to be in my denominator, and I'll have 0.974 atmospheres. Okay. Okay, so 0.974 atmospheres. In terms of the moles, I have the moles from up here, so 0.014. R, I'm going to use with atmospheres, so R is 0.0821 liter atmospheres per mole Kelvin. And then the number of Kelvin, 24 plus 273 is 297. So 297 Kelvin. Okay, and there we go. And now we've got it all set up. It's kind of messy in terms of the writing, but there it is. Let's see what we can do. 0.014 times 0.0821 times 297 divided by 0.974. So 0.350 liters. Okay. And there you go. So that's the ugliest of the problems. And technically, you can solve almost any of the problems like that, because I've given you temperature and pressure, even if I've given you standard temperature and pressure. Okay. So in this case, right, if I'm starting with volume, I need moles. So in this case, I'm going to find moles. I'm going to go backwards, right, from what I did before. So N must equal PV over RT, right? And so I'm going to use that as my initial equation. And then I'll take those moles of carbon dioxide, moles of carbon dioxide, and I'll simply use cancel moles of CO2, right, and get moles of magnesium. And then I would simply use the molar mass, right, to cancel moles of magnesium and get grams of magnesium. And that would be my final answer. So whatever I get from here in terms of moles will go in the front here. Okay, so we've set up that idea, right? Now, in this case, moles, the pressure we have is at 105 kPa. So my temptation is to simply leave 105 kPa times 15 degrees Celsius, which is 288 Kelvin. And then I would divide it by R, and I would, instead of using 0.0821, I'd use 8.315, because that has the kilopascals. Right? and then times 2. Why did I put 288 in the numerator? What's up with you? Can't believe you guys didn't complain. Please don't do that. The volume, I say, 2.5 liters. 288 Kelvin. Okay. And so we'd get an answer here. That answer would then get plugged in over here. Okay. And that would get you all the way through. In terms of the mole ratio, if we look at the chemical equation, there are 2 moles of magnesium for every 1 mole of CO2. And then the molar mass of magnesium from the periodic table is 24.31. Right? And 1 mole. And there it is. So that's set up. Okay. Well, I would like you to try the other 2 on your own. The other 2 are, again, following the same patterns from the notes. So you have one that is volume to volume, right? So it works just like this first one. And then the other one is also volume to volume, but you'll follow it up by using the 22.4 ratio to convert volume to moles so you can figure out the amount of the other substance. Okay. So try solving these guys on your own. And if you can work in groups. If you can, then Yahtzee, we are done for today.